The selection committee is pleased to name Dr. Morgan Kelly, a 2022 Frederick A. Howes Scholar in Computational Science. Morgan earned a PhD in chemical engineering in August 2021 under the supervision of Professors Michael Baldea and Ross Baldick from the University of Texas at Austin. After graduation, she joined Dell Technologies as a data scientist. Morgan's selection as a Howes Scholar reflects both her exceptional technical achievements as well as her demonstrated leadership and character. Morgan's doctoral thesis research developed methods to enable large-scale integration of renewable power generation in the operation of the grid, focusing specifically on enabling large-scale industrial electricity consumers, for instance, chemical plants, to implement demand response strategies. During her doctoral program, Morgan made definitive contributions to multiple long-standing challenges across the renewable energy landscape. On the consumer side, she developed ways for plant operators to determine optimal production schedules given much more frequent changes in plant operation. Her data-driven approaches allow extraction of the key dynamics of scheduling relevant plant dynamics. On the production side, her research developed vital new ways for grid operators to accurately represent plants' energy storage capabilities, resolving the challenge of how to do so without exposing business-sensitive or competitive information. On the practical computational side, she also developed a transformative approach to solving demand response optimization problems. Where previous approaches were so computationally expensive as to be largely intractable, Morgan reformulated the difficult nonlinear optimization problem into a mixed integer linear program, obtaining an exact equivalent that reduced calculation times by orders of magnitude and made practical implementation feasible. See David's talk this morning. Together, these contributions demonstrate a breadth of expertise that spans from seminal theoretical contributions to data-driven methods and high-performance computing for real-time industrial decision-making. Morgan has also distinguished herself through service and leadership to the community at large. She dedicated significant effort to her volunteering at a food bank. Within her graduate program, she developed and implemented the optimization method used to match incoming graduate students and advisors given sets of preferences. Furthermore, she organized a seminar series for early-stage PhD students. With her graduate advisors group, she mentored both undergraduate researchers and graduate students, with significant impacts on their research capabilities and productivity. She also took on the central role in advancing her advisors' activities, engaging middle school students to pursue STEM careers as first-generation college students. Finally, Morgan has repeatedly shown fearlessness, initiative, and leadership in translating her research efforts to real-world practice. For instance, she sought out and established a collaboration with the world's largest industrial gas company, working across organizational boundaries and coordinating among stakeholders to establish that her methods offer substantial advantages in real-world operational settings. Morgan Kelly is a computational scientist who not only excels technically, but also takes on leadership roles in the scientific community and society at large. She embodies the qualities Fred Howes promoted in all early career scientists. Congratulations.
Very natural. Hi, so I'm Morgan Kelly. Today I'll be talking about dynamic modeling and optimal scheduling of chemical processes that are participating in fast-changing electricity markets. I will primarily be focusing on a data-driven approach. So day-to-day, this is kind of what the grid looks like. So this is a 3-day time period in July, and this is in California. So typically our demand peaks in the late afternoon hours to early evening. So this is the hottest time of the day. This is when we're also coming home from work and we're maybe starting the dishwasher, cooking, doing laundry, ramping up the air conditioner, things like that. If you look at the bottom of this plot in red, we see where renewables peak, which in a place like California with a lot of sunshine, this is actually during the daytime hours, so when there's a lot of solar power on the grid. Unfortunately, this is just a little bit offset with when we use the most electricity. So the difference between when renewables are available and demand, I've labeled here as the deficit. So this kind of actually directly drives our electricity prices. So here are the electricity prices over that same 3-day period. As you can see, the peaks pretty much align. So the idea is that if we can shift our usage to when renewables are most available, we can save money and also reduce the amount of fossil fuels. So those prices are actually driven by the grid needing to purchase additional fuels, such as gas imports and things like that. So here is an extreme weather example of what exactly happens in a deregulated market. So in February 2021, Texas had a pretty severe snowstorm, central Texas, so this is Austin. We had over 140 hours below freezing and 6.5 inches of snow in a subtropical climate. So this is my dog for scale. It was a lot of snow. I'm from Arizona, so I'm just very unfamiliar with snow in general. So if we take a look at what happened on the grid over that time period, so I've shown the 11th, 12th, and 13th here for kind of a reference. The snow happened on the night of February 14th. So if we look here, I don't think the laser works too well, but if we look at this period here, we see that our grid load is below capacity for the most part, and our capacity tries to stay just above load. So in case there's any unforeseen spikes in our demand, the grid can actually meet that demand. Now you'll see here on the 14th that our capacity starts to climb, as does the load. So they are expecting that this weather's gonna come. They're ramping up capacity. This blue line right here, you can't even really see what price it is on these days because it's so low in comparison to how high it got. So essentially, when the snow hits here, we see that our capacity actually dips below the demand. And given that we usually want to have quite a bit of overhead gap between those two, the fact that it dips below is a huge problem. And so you see here that the prices start to climb even before that happens, getting all the way up to about $9,500 per megawatt hour. Typically in Texas, at this time of year, there may be around like 12, 15 dollars per megawatt hour. So this is huge. So people that participated in demand response, residential demand response, actually got hit with massive electricity bills during this snowstorm, just like actually absurd. So the other thing Texas will do to kind of curb this demand so we can get capacity back up is they'll do something called a rolling blackout. So they'll shut your power off for 10, 20 minutes and get the grid back up and rotate. The problem during the storm when they did this is that the grid wasn't winterized, and so they actually couldn't get the power back on. So they turned people's power off, then it was stuck off. So that's why you see here, our load actually decreases quite a lot, and that's not because people weren't needing electricity, it's because they didn't have it. So it's an issue. So it's not really fair, I think, to rely on residential consumers to kind of help the grid demand, because in this scenario, like having heating or gas, that's like life or death, right? So you don't really want to ask residential consumers to do this. Obviously, this is like a very extreme scenario. With climate change, like these things are going to happen more and more often. So it's good to keep this in mind. What we can do is actually turn to industrial consumers because they have a much more flexible load. Like they don't necessarily need to be operating during a snowstorm or an extreme heat event or even on a hot afternoon when there's a lot of electricity demand. So the idea is that we can actually use chemical plants as batteries. So if they can overproduce when prices are cheap or capacity is low or capacity is high, they can store their previously used product and use it to meet demand when capacity dips low or prices dip high and things like that. So not only can they help the grid, but they can also save money, which for an industrial consumer is their goal. For better or worse, like you need to save money when you operate. So here's kind of what that looks like. So on top we have a planning layer, and this is actually our product demand forecast. So this would happen on the chemical plant side. Their production scheduling here will take into account electricity prices and ambient conditions, so they can be forecasted prices either based on the day before or based on the weather, things like that. So it feeds the optimal production sequence to this control layer, which then gives instructions to the plant. So it will say, okay, we're gonna put production at this level for these hours because electricity is gonna be really cheap and things like that. The issue with this is it takes several different time scales. So your plant is gonna be changing every second. The control layer might give different commands every hour or minute. The planning is obviously gonna happen on the scale of months, and then your electricity prices are gonna change depending on every 15 minutes or every hour or once a day and things like that, just depending on what plan you select. So this becomes a pretty complicated computational problem. But in general, the idea is that we can shift our demand here using paired events. So we need to do frequent scheduling changes. Electricity prices can change pretty quickly. We want to make sure it's safe for the plant. So in a chemical plant, like things going haywire can be quite dangerous. Things, exploding, overflowing, or just you're giving an impure product to customers. So we make some assumptions. We assume that whatever product we're making can be safely and effectively stored. So this is saying, yeah, we can store our product. It's not going to gas off. It's not going to get impure. It's not going to explode. It's not going to be prohibitively expensive to store. And that we're able to make fast transitions. So Essentially, the goal is to do these fast calculations in less than an hour, ideally less than 15 minutes, so we can play in the 15-minute electricity market. We want an MILP, so a mixed integer linear program, because these are the models that the grid is on, and so we want to make sure our models are compatible. These are typically favored in scheduling problems anyways, and there are many fast commercial solvers available. So this is kind of what this would look like. Our purple line here is our set point for the plant, so that is the control instructions. And the orange line is what the plant might do to follow those instructions. So as you can see here, our instructions, the purple line, are actually changing before the orange line actually reaches that recommended instruction. So these changes are actually happening faster than the plant can catch up. And so we need to make sure we have a really, really good prediction of the plant so we know that we're not going to violate any constraints as we move forward, because this is all happening very quickly. So essentially, we're combining two time horizons, our control horizon, which we're going to assume is every hour, and our plant horizon, which is either on the scale of minutes to hours, depending on how fast that variable moves. So something like a temperature might change quite slowly given the heat transfer, but an impurity might happen pretty quick. So these models are nonlinear, stiff, and high dimensional. So this is kind of what that will look like here. So we have our scheduling time grid here, and our dynamics time grid represented by index J. And again, we're just looking at this bottom part of the model. So to model this, I've chosen to use scale bridging models. So these are low order, and they utilize input-output data. So we actually don't need to know what happens between the input and the output of the process. This is especially good when working with industry partners, because they might not want to tell you everything their process is doing, but they still want to participate in something like this. So we actually only capture scheduling relevant variables, so this does help us to slim down the model. So maybe like an intermediate temperature isn't that important for the overall schedule and production of the plant. So essentially, we have our scheduling layer here. Our set point targets are fed into the scale bridging model, and we get our output quality variables. And so this basically loops together those two bottom blocks in the diagram I've been showing. So this is kind of what the problem looks like, and we can think about this basically in the context of real life. So our time that we see is continuous. A computer's time, especially in a mixed integer linear program, is going to be discrete. So say I was walking across the room, and a minute passed, and then I ended up in a totally different spot, right? Because I didn't tell my problem where I was in the previous minute. So we have to ensure that where we were in the hour before, that last second has to be equal to where we begin in the next hour. So we're essentially setting a new initial condition for every time. However, these complicating or continuity constraints actually add a lot of computational issues because we have to solve these problems sequentially. We have to say, okay, we're solving for hour 1, what was the result? Now let's solve for hour 2. If you're doing multiple day time horizons, so in this, I'll typically do 3 days, so that's 72 problems you can't solve at once. You have to solve them in a row. And you're solving for every second within the problem, so that can become really, really slow. So what I've done here is to actually get rid of the complicating or continuity constraints and actually penalize them on the objective. So say I was walking across the room, a minute passed, I'm over there. Well, now I basically subtract how many feet away I am from where I'm supposed to be, and then that is what's got added onto the objective, and so we're basically penalizing, so it's turning it into a soft constraint, which actually enables us to use parallel computing to solve each of these sub-problems separately and kind of come back and check how we did. So this is called Lagrangian relaxation. Essentially, we solve a relaxed subproblem, which is where the continuity constraints are removed. We calculate these parameters, which are basically how much have we violated where we should be versus where we are, and we penalize that on the objective function up here. And basically, we just keep iterating until we get a solution. And with linear problems, there's actually a theorem that shows that your solution to the relaxed problem is actually mathematically equivalent to the original problem so long as a solution exists. Which for a linear problem, a solution does exist, and so that's huge, which means we can actually parallelize something without any drawbacks, essentially, like we're not losing any model fidelity. So I'll show the first example is more small scale. So this is a cryogenic air separation unit. Essentially, we had a first order full principles model. So essentially, we did all the PDEs and differential equations, all the fluid flow in this whole plant. And we generated a set of data off of this. So up to now, there was no industry participation directly. So industrial air separation is actually a really good company for demand response because they have one feed, and that's air, which is freely available, and the other feed is electricity. And so they're really high energy consumers. You have to liquefy air to separate it. And so the products of this one were liquid and gaseous nitrogen. And we have these liquefier, which is for the storage. So the liquefier is actually an add-on when you do demand response, though typically they have one already because a lot of these gases are transported as liquids in the first place. And then this inlet compressor, and these two turbines help to offset the electricity usage, but not by a whole lot. And as I said before, the longer time horizon you do, the more savings you have because you're able to better utilize storage. So if you can use something on day 3 that you stored in day 1, you have that many more days to kind of benefit yourself in terms of electricity prices. So in this case, we'll use a 3-day time period. So here's some results for the small scale case study. So this top model is full order. That was the initial differential equation model. All of these are on a normal computer. So if you were to solve it on the laptop sitting in front of you. So that first one took about 95 hours to solve. Given we have a 3-day time horizon, that's not really useful at all. So that's kind of where it started. And then the second one is a nonlinear scale bridging model, so something like a polynomial model. And that took about 5 hours, so a significant improvement just using a scale bridging model versus a full order model. You see we save a bit more with the full order model, and that's just because we don't have to use any back-off constraints then. With the scale bridging models, you have to say, okay, our purity needs to be below 2,000 parts per million, but actually we're going to put the bound at 1,800 just so we have a little bit of leeway if there's model mismatch. Then if we look down here at our discrete models, so this is again where we use the different discrete time to represent the model. We see that without the Lagrangian relaxation, it took 11 minutes, still a great time. With it, it took about 7 minutes. And just as expected, we have the exact same solution, which is great. We have anecdotally proven the proof. And then just to give an idea of the size of these problems, so P3, which is the discrete scale bridging model with no parallelization, is about 85,000 variables, and then some integers as well. P4, which is with the relaxation, there are more variables because now we have that penalty variable. However, the overhead for more variables is still not as good as the achievements we've gotten with parallelizing. So it doesn't matter that we've added more variables in this case. So these are the power requirements, just to kind of tie it back to the grid. Our overall, we had an increase in electricity use, which makes sense. We're using the liquefier a little bit more to liquefy our gas so we can store it. However, we've decreased our peak demand by about 20%. So in a case, especially like in Texas, California, you do have a lot of stress on the grid. You're actually able to significantly shift that peak a little bit, hopefully cut residential consumers a little bit of a break. So yeah, we can see here kind of what the different plans do. In general, they're pretty much the opposite of electricity prices. So as electricity prices go down, the production levels go up in power consumption, and then we get this lower dip here. So this is just a toy model. We then took this and applied it to a real plant as well, which I will talk about. And then in general, these air separation units operate in a network. And so the idea is to get multiples of these, and then you have not only the amount of product, but also where it's located, and so that adds a little bit of complexity there. So this is an industrial case study. So this was done with Linde Corporation. So in this, we have a few more products. We have oxygen, both liquid and gas. We have argon, and then liquid and gaseous nitrogen as before. This plant is a lot more complex than our toy model. We had a year's worth of data, so think about every second in a year times however many variables they gave us. That was a lot of data, which is great in terms of fitting a model, but it's also just a lot to look through and clean and things like that. So we used an autoregressive model with an extra term, which for those of you who have taken controls courses or in more engineering cases, you might recognize this. It's a pole zero model. So essentially, you have your inputs U here, a series of equations, and then your outputs Y. So this model is linear. However, it does, depending on the order, it looks back more than just one point in time. So now I'm walking across the room. For the problem to know where I'm going to be at the next hour, it's actually going to get the previous 5 steps I took. So it's able to be linear because of this, but also there's a lot more complicating constraints. So this is kind of what we had before, a traditional block angular structure linked at one point. Now when we use, which had one complicating constraint here, we've reformulated any nonlinearities, so that's kind of what we did in the toy model. That just wasn't possible with the industrial data. Like those models were so high order, they just wouldn't solve. So now we've used these autoregressive models. So instead of one initial condition, we've got, say it's a fifth order model, we now have 5 initial conditions. So there's a lot more overlap here between this. So now we're looking back more time steps. However, this model is linear already. We don't need to linearize it. We don't need to add integer variables. So we're actually going to see that that's pretty beneficial. A key challenge I found that I wanted to include with this industrial data is that measurements are not perfect. I spent probably like 2 months trying to figure out what was going on. We had our mass balances of the chemical plant, which essentially is N equals to out minus whatever you've lost. Nothing matched up. And so we were like, what's wrong with the data? What's wrong with the equations? What's going on? My models aren't fitting. It turned out that the plant sensors were broken. And so that was something that was new to me, which in looking back, I'm like, yeah, that should have been obvious, but it wasn't, so I'm just telling everyone here. Yeah, so essentially what we did is we generated these scale bridging models for the error in the sensors. So that we were able to get our mass balances closed. We were able to account for a leak in the system, which wasn't a physical leak, but it was just a measurement leak. So yeah, I thought that was pretty cool. It also, I spent a lot of time on it, so I was like, I should include it. And then yeah, so here are the model fits after we were able to model the error. So they are really good. The normalized mean square error is quite small for both training and test. And we used our process knowledge to select these inputs. So we have 3 power consumptions here. We have our flow of our products, and then some unspecified control variable as well. The rest of the variables, we kind of sorted out through PCA that we actually didn't need them to predict the outputs. So we threw those away because time is of the essence when we're solving these problems. So here's a model here. Everything is scaled to the upper and lower bounds. So this would be like a year's worth of data, or maybe this was just our training data. So yeah, here we have kind of what that looks like. The gray is the model, and the blue is our fit to it. So it's pretty good. And then this is the optimal schedule we came up with. Now everything is scaled between the upper and lower bounds. So these axes don't really mean anything. Something interesting we found using a linear model now is that we get these bang-bang solutions, so on-off, right? So this is the flow of, I can't read that, gaseous nitrogen. And so it basically goes from the lower bound to the upper bound, back and forth, back and forth. That's not really realistic for a plant. For the nitrogen, it ended up being okay, but we actually had the same thing down here with the argon. So we had to add in these rate of change constraints, which say, okay, we get that the model thinks you can do this, but there's obviously some shortcomings with these scale bridging models, and we're not taking into account everything. So we're setting a rate of change constraint here. And so that kind of helps. And this, we got a cost savings of 8.9%, so this is compared to not using demand response. And then a computation time of under 2 minutes, which is huge, considering this was like a true industrial problem. So in practice, using these models and fitting them is very difficult. So something we want to do is use transfer learning. So ideally, we take a model that's fit on a previous plant, use it on a new one, and actually update the parameters using Kalman filtering. And we've done that here, and that's kind of what that looks like. We get huge improvements in fit, and this kind of just is an iterative process. So something here that we did additionally, near and dear to my heart, is grid-based emissions. So the idea is not only can we look at prices, but we can look at emissions on the grid. So say there's imports and fossil fuels are quite high. We can actually see that it somewhat correlates with price. So our emissions are highest. They peak around the same time as price, but they last much longer. So if we solve demand response problems, we actually see that we, for the most part, are able to consistently reduce emissions, even though our aim is to reduce cost, and that's because there's some parity between the emissions peak and the electricity prices. However, if we see that if we change our goal to minimizing our emissions, we actually will get a more expensive solution in the summer months, which industry is not really going to go for. So we did this just to kind of see, what would happen, and this is for a whole year's worth of problems. So this was like three-day time periods per month, basically, for a whole year of electricity prices. So for conclusions, demand response has potential for mitigating grid instability and reducing emissions while saving electricity costs for companies. It involves little to no capital expenditure, and primary involves changing in operating habits, which is huge. A big thing is like convincing people that your work is useful and not a big hindrance to them. And so, yeah, I mean, I'm sure you guys know that. And recent advances in computer technologies, models, and algorithms do enable the efficient solution of these problems, which were not able to be efficiently solved before. And future work would be time of use electricity pricing for residential commercial entities. People are doing this. My group typically focused on industrial consumers. It does have a potential, I think, to play a role in remote computing tasks. So since I've been at Dell, this is something I'm thinking about, is that we can schedule runtime and location of large problems with a flexible load. So you use your credit card, they process those transactions all overnight, and that's a pretty big compute that these banks are doing. So now we can think, is there a better time of day to be doing that? And likewise, we could even change the location of where these transactions are occurring. So sending a packet of data might use less energy than solving the problem somewhere where there's a lot of fossil fuels on the grid versus where there's renewables. So that's just something to keep in mind. And yeah, a big thank you to the DOE CSGF family and my research group and my dogs.